And then we talked about the two frequencies, lower frequency and the higher frequency. That is the two frequencies between which we decide whether it's a band pass filter, band stop filter. Okay. Now you have already done that, so we will just first do some of the problems regarding that calculation of your resonance, calculation of your bandwidth, and calculation of this selectivity, and then we will move on to the parallel circuits, the parallel resonance circuit. Okay, so just let's start off. Okay, so I think I'm sharing the section. Just a second. Okay, so let's start off with an easy problem. I'm just sharing this. I think everybody do this. Everybody do this problem, and after you finish, you tell me what is your answer and what are the steps that you have. What are the steps or the sequential steps? You can say that to me, or if you want, you can share your solution to my WhatsApp as well. Okay. So please focus on this problem, everybody. Where you have been given an AC circuit, you are having a resistance of 100 ohms, an inductance of 1 Henry, and a capacitor of 1 microfarad. So you have to calculate the resonant frequency and the voltage across each element when the supply voltage is 50 volt. Okay, do this numerical, everybody. Do this 5.46. Please note down the numerical. You are having a resistance of 100 ohm, inductance of 1 Henry in series with a capacitor of capacitance 1 microfarad. You have to calculate the resonant frequency. You know already the formula of resonant frequency. And you have to calculate the current at the resonant frequency and the voltage across each element when the supply voltage is 50 volts. Okay, so do this. Okay, please do this numerical. Let me know when you have completed. Calculate the resonant frequency by the formula 1 by 2 pi root over LC. First you calculate the resonant frequency. Anybody did have done this? Anybody completed this?
Is it 318 hertz?
Repeat just. Hello?
318.
Yes, 318 is the resonant frequency. Then you continue next. Just put 1 by 2 pi root over LC. 318 is not 318. Just check, man. This is 159 hertz. See? 1 by 2 pi into root over LC. So your 1 into 1 10 to the power minus 6 and 2 pi, that is 2 into 3.142. So please check this.
Yes, yes.
It is 159 hertz. Okay.
Yes.
Okay. Next is
Yes, sir.
what?
159.
Yes. So what will be the current? So you already know that when I am talking about resonant condition, the that is the inductive reactance and the capacitive reactances are equal. So your XL minus XC becomes equal to 0. So your impedance Z, that will be equal to R. Impedance Z will be equal to R. So when you are calculating the current at resonant condition, that current will be just voltage divided by the resistance. So the voltage divided by the resistance, you are getting the current at resonant frequency. So this is the concept. Yes, this has been written at this, but when you do in your problems, please mention that at resonant condition, the inductive reactance is equal to the capacitive reactance. So impedance is frequency is V by R. Okay. Now next what you have to calculate is the voltage across each element when the supply voltage is 50 volt. Right. So this also I have explained. Resistance will be same as the voltage across the or the main voltage supply. The voltage across the resistance will be same as the main voltage supply, since the voltage across the inductance and the voltage across the capacitance, they are equal and in opposite phase to each other. This I have explained last day, that the voltage across the inductance and the voltage across the capacitance phase to each other. So when you are calculating voltage across inductance and capacitance, you will see that the voltage is coming out to be same as 500 volt. But when you draw the phasors, that will be in opposition to each other. And the voltage across the resistance will be same as the supply voltage. So that will be equal to 50 volt. So this is how you calculate 500 volt, and the voltage across the resistance will be equal to 50 volt, that is equal to the supply voltage at resonant condition. Okay, so this is it. Any doubt, anybody, from this question? All of you have understood? Right. So we move on to the next question. So next question, what we will do, so let's do this. So let's do 5.49. Everybody please do 5.49. Everybody please do 5.49. Please read the question, what it has been given. It is given a constant voltage at a frequency of 1 megahertz is applied to an inductor in series with a variable capacitor. Okay. So when the capacitor is set at 500 picofarad, the current has its maximum value and it is reduced to half when its maximum value of the capacitance is equal to 600 picofarad. Okay. given it is maximum at 500 picofarad, and it is given it is it's reduced to half of its maximum when the capacitance is 600 picofarad. So you have to calculate the resistance, the inductance, and the Q factor of the inductor, right? Is the question clear to you? Then we move on to the solution. You have been given a constant frequency of 1 megahertz, that is 10 to the power 6 hertz. This is being applied to an inductor in series with a variable capacitor. So what is a variable capacitor? That is for which you can vary the value. Now, when the capacitor is at 500 value, so when is the current at maximum value? So you know at resonant frequency, at FR, current will be maximum. At FR, your current is maximum. So when you are calculating FR, you need to use the inductor value and this capacitor value. Inductor value and this capacitor value. So let's see how the problem has been solved. So first it is said the current is maximum at resonant frequency, which is equal to F0, and that is equal to 10 to the power 6 hertz. F0 is equal to 10 to the power 6 hertz. 1 megahertz it has been given. So at 1 megahertz your current is maximum. Your value of the capacitor is given as 500 picofarad. So you can do this. F0 is 1 by 2 pi root over LC. You can calculate L. So your L will be equal to something 10 to the power 6 by 2 pi into root over 500 L equals to 10 to the power 6. If you calculate this entire thing, this will come out to be 0.05H millihenry. 0.05H millihenry. Is this clear? So it has been given that you have a frequency of 10 to the power 6 megahertz or 10 to the power 6 hertz, at which the current is maximum and the capacitance value is 500 picofarad. Pico is 10 to the power minus 12. Okay, so from that you calculate the value of the inductance, right? Okay.
So is it 500 or 600?
Which one?
The capacitance value?
See, it is given when the capacitor is at 500 picofarad, the current has its maximum value. So when is the current value maximum? So at resonance. So at resonance condition, the capacitance value will be 500 picofarad.
Yes. Thank you, sir.
Okay. So this is the value of your inductance. Okay. Now next what we do, we move on to the second part. So the second part states that the capacitance value is 600 picofarad. So at this condition, your current is equal to the resonant current, that is the maximum current by 2, right? The maximum current by 2, half of the maximum current. So your frequency is 10 to the power 6 itself. Your capacitance value is this. So we find out the value of the capacitive reactance. Right? Okay. We have got the value of the inductor as 0.05 millihenry. So we calculate the inductive reactance. Please focus on this. First, by taking the value of capacitance frequency as 10 to the power 6 hertz, we have calculated the value of the inductance, right? This inductance value is constant. Because the inductor is constant, the capacitor is variable. So for capacitor value of 600 into 10 to the power minus 12, we calculate the capacitive reactance. And at the same point or at the same frequency, we calculate the inductive reactance value. Okay, this is coming out to be 314 ohm. So what is your net reactance? Net reactance to 49 ohms. XL minus XC, that is equal to 49 ohm. The net reactance is 49 ohms. Okay, is this clear? Next, what did I say? Your I is equal to I0 by 2. So at resonant condition, what is your I0? Your I0 is only V by R. This is the maximum, is equal to R. Therefore, I0 will be equal to V by R. Right? So, when you write this expression, I is equal to I0 by 2, along with that, you replace I0 by V by R. So, this becomes equal to V by 2R. I0 is V by R. So, I is becoming V by 2R. Okay. Now, you consider this case. So, your I is equal to V by 2R. Again, I is also equal to V by Z. So, what is Z? Z is this expression. Root over R square plus XL minus XC whole square. So, what is your equation becoming from the given problem? You know I is equal to V by 2R. And again, I is equal to V by Z. That is V by root over R square plus XL minus XC whole square. So, you equate these two. See, V and V gets cancelled. You cross multiply. So, you are left with 2R is equal to R square plus XL minus XC whole square. And then you just calculate this. So, this value you already know. Here you have calculated this as 49. So, this is coming out as 49 square. Okay. You have squared up both the sides. 4R square is equals to R square plus 49 whole square. And then from this you get the value of the resistance. Okay. You get the value of the resistance. And what is the value? What is the formula for Q factor of inductor? This we have already studied. XL by R. So XL at resonance condition. So that is why we have written it XL is equals to omega 0 L by R. You calculate this, the Q factor is coming out to be 11.1. So that is the voltage across the inductor will be 11.1 times the voltage across the resistance. You can calculate this by your technique or by just putting the formulas as well. You will see that the Q factor of the inductor, will be 11.1 times, or that means the voltage across the inductor will be 11.1 times that of the voltage across the resistance. Okay. So this is a typical problem where you need to apply the concept of Q factor and resonance. Okay. Do you need to note it down? So you can note it down, or if you can do this on your own, that is also fine. Please note down the problem because this problem is important. One kind of an important problem. You can have problems like this. So please note down the problem. Anybody is having any doubts, you can ask me.
So can you explain how I is equal to V by 2R again?
Yeah, sure. See, it has been given. See, look at the problem. It has been given that I is at 600 picofarad. The current is reduced to half of its maximum value. Okay. So what is the maximum current? So the maximum current is the current at resonance condition. So the current at resonance condition, if I represent it as I0, so at resonant condition, your XL is equal to XC. So therefore, your impedance is equal to R. Okay. So what is I0? I0 will be voltage divided by Z, that is voltage divided by R at resonant condition. Now at 600 picofarad it has been given, so at 600 it has been given that I is equal to I0 by 2. See, half of its maximum value. So this was your maximum value. Since at resonant condition the current is maximum, I0 with V by R. So half into V by R. So that is equal to V by 2R. This is from the given problem. Okay. This is from the given statement of the problem.
Yes, sir. Thank you, sir.
Again, V, you know already that I will be equals to V by Z. So we are just equating these two. Okay?
Yes, sir.
Right. So now next, you look at this problem 5.50. Look at this problem. Here also you have been given the two cutoff frequencies. You are given a resistance at resonant condition. So you have to calculate the resonant frequency, the value of R, L and C, and the quality factor at resonant frequency. You have been given that the impedance is 500 ohm concepts, and you have been given F1 as 10 kilohertz, F2 as 100 kilohertz. Okay, so from this you can calculate bandwidth. You can calculate bandwidth. So what will be bandwidth? F2 minus F1. And what is the formula of bandwidth? This is equal to R by 2 pi L, right? So from this you do this problem. Please try on your own, or else I will show the problem. Put the concepts that are at resonance condition. At resonant condition, the impedance value is equal to your resistance value. So from that you can calculate the value of the resistance. When you put it in the value of the inductance, you will get the put it in the value of the bandwidth, you will get the value of the inductance. So like this, you please try this out. Please try this out.
Yes, sir. FO. Yes, sir.
Resonant frequency is
55.
55 kilohertz. Yes.
Yes.
55 kilohertz. Yes. Okay. Do the next. Do the others. Sorry. Do the others.
too small.
What is it coming? The value of C? The value of C is 0.095 in 10 to the power minus 7 farad. This one. See, F1 is
Yes.
F0. You use any of these formulas, no issues. You will finally get to F0. Okay. You will finally get to F0. Your F0 is just midway between F1 and F2. So what else you can do? You can just add F1 and F2 and divide it by 2. If you have seen the graph last day, your graph looked like this, right? So this was your F1 and F2. So let's say this is your F1 and this is your F2. Okay. So this was your F1 and F2 and this was your resonant frequency. So this is F1, this is F2. You can use this formula. You can use this formula, or else you can just do F0 is equal to F1 plus F2 by 2. That also is fine. So from that you will get the resonant frequency. So once you get the resonant frequency, you can calculate C from that. You can calculate C from that and you will get the value of C as, say, something like this. Next, you have to calculate the Q factor. Q factor is nothing but omega 0 L by R. Omega 0 L by R. So from that, you calculate the Q factor. So what is the Q factor suggesting? That is the voltage across the inductor and the capacitance is 6 times that of the voltage across the resistance. Okay. And what else you have been asked to do? You have been asked to find out the power factor of the circuit. So see, I explained this last day itself that the power factor of the circuit at resonant condition is equal to 1. Is equal to 1 because your reactance, net reactance is 0. Net reactance is 0. So your impedance is equal to the resistance. So the power factor of any circuit at resonance condition will always be equal to 1. So you need not calculate this. What was important was calculating this resonant frequency from this F1 and F2. Okay. So this is the step. So first you calculate your at resonance condition resistance is equal to the impedance. From that you get R. Then you put into this value bandwidth is equal to R by 2 pi L. From that you get the value of L. Then you calculate the value of F0 from the formula F1 is equals to F0 minus R by 4 pi L. From that you calculate C and Q factor, and power factor will be always equal to 1. So this problem is an application of bandwidth, this cutoff frequencies, all this. Now if you are asked to calculate, say let's say you are given a problem where you have to you are asked to calculate the frequencies of a band pass filter. Frequencies of band pass, that is, if all other parameters like L, like C, R, if these parameters are given, what you need to calculate is F1 and F2. So what will be F1 and F2? That is F0 plus, and F0 you can calculate from these two values. So F1 and F2 will be this. So if you are asked to design or if you are said that you design a band pass filter, or you have to design a band pass filter and what are the passing bands, then you have to just determine F1 and F2. Similarly, if you are asked to determine a band reject filter, then you have to determine the F1 and F2 or the frequency bands for which the filter does not work, or the frequencies that are stopped by the band. So everything is related to this F1 and F2. And one more thing that did not do here is the calculation of the selectivity. See, for this problem as well, I did say that this is the half power frequencies, the cutoff frequencies are the half power frequencies, because at this condition the power is half and the current is equal to I0 by root 2. I said this. So when you are talking about the half power frequencies, that is also F1 and F2. So you can calculate this when these parameters are given to you. And one more thing is the calculation of selectivity. So this has not been shown here, or no problem has been given here, but for selectivity case you have to imply this equation. For selectivity you have to imply this formula. Okay. So all this is related to this F2 and F1. And what is F1? This thing is F1 and this thing is F2. So all this thing is related to F1, F2, bandwidth and selectivity, right? So this is the parameters that you use to calculate while you are designing a band pass filter or a band reject filter. Okay, so this is all about your series resonance and the series filters. Series resonance and the series filter. So I will just show you two things before I close off the class. Okay, just two things I will show you. Just 1 minute I will take. That is, how does a series, is this visible to you? Okay, so just look at this. This is the structure of a band pass filter. This is the structure of a band pass series filter. So series resonant filter, which is a band pass filter, the structure is like this. Okay, and it allows all the frequency bands to pass between F1 and F2. So this point is F1 and this point is F2, right? So this allows F2. So see, this is not starting up from 0. This is starting off somewhere here and it is ending somewhere here. So this is the structure of a band pass filter. Please, you can draw it or you can note it down. The structure of a band pass filter. And this is the structure of a band reject filter. This band is the stop band. This band is a stop band, band stop or band reject filter. So at this point, no frequencies between this frequency range is allowed to pass through. So we tell this as a band stop or a notch filter. Band stop or a notch filter. Okay. So please note it down. This is the structure of a resonant circuit or a resonant band stop filter, and this is the structure of a band reject filter. Just see the orientations. Band pass L and C in series in horizontal condition with R, and here L and C between the output terminals and V is within the input terminal. Okay, these are the structural differences between the band pass and the band stop filter. So this comes like, say, 2 marks question. Draw the circuit of a band pass filter. So you have to draw. So we stop here today. Monday's class will be taken again by Somnath sir. I will take your class on Tuesday again. Okay. So I am giving your attendance. I think only one person is absent today, and that is Shubhradeep. I do not find Shubhradeep here. And please join the poster competition link at 3 p.m. Just after your class gets over, join the poster competition link. Okay. So now you can leave the meeting. If you have no questions, you can leave the meeting. Okay. Thank you.